Okay, we're going to talk about motors and motor currents and how these motors operate. Okay, right here you have the nameplate. The nameplate on an induction motor, on any motor, tells you the voltage it's going to operate at, tells you the RPM it's built for, tells you what full load current is, tells you the frame. This is a 56C frame. It tells you how high the shaft is to the center, tells you what diameter the shaft is. It tells you the bolt hole pattern. So a 156C motor will fit where another 56C motor is. Doesn't matter. It could be a Baldor, a US motor. It could be a Square D. It could be any of them. If it's a 56C frame, it's going to fit. Now, motors are built for a certain speed. So a two-pole motor runs at 3,600 RPM synchronous speed. We've got two different speeds, synchronous and actual, and I'm going to talk about that here in a minute. Okay, so on synchronous, two-pole motors 3,600 RPM, four-pole motors 1,800 RPM, six-pole motors 1,200 RPM. I'll have this written out and put on blackboard. Please, please, please memorize this. I know it's on every stinking electrical test that I ever took. Okay, now let's talk about currents and how currents work. We'll move this over here and we'll pull the rotor out. This is a squirrel cage rotor. It has laminations here, but you see these two aluminum rings here. These are shorting rings. Then you have aluminum bars that run across from ring to ring. You should remember what a squirrel cage looks like from rotating equipment. You need three things to generate a voltage and or a current. You need a magnetic field, you need a conductor, and you need motion. Okay? The motion the conductor are these bars running from shorting ring to shorting ring. That's your conductor. Okay? Now we'll set this aside. Your windings here provide the magnetic field. So when you apply power to your motor here, you're going to have a synchronous rotating field here for a two-pole motor. It's going to run around 3,600 RPM. It's going to be invisible, but that's what it's doing. 1,800 for a four-pole, 1,200 for a six-pole. There's your rotating field, okay? That's your motion, okay? So, and that's also your flux. Your flux and motion comes from your windings. Now, when I put the shaft in here, the more magnetic lines of force you cut, the higher your current's going to be. This is a rotating transformer. That's all it is, rotating transformer. This is your primary, this is your secondary, okay? Now, remember, conductor, magnetic field, and motion. Here's your conductor. The squirrel cage is up inside here. Your motion is up inside here, the magnetic field going around. This here is a four-pole motor, 1,800 RPM. Now, when I stick this rotor in here, when we apply power, at the instant we apply power, we have a rotating field here of 1,800 RPMs, but a shaft speed of 0. So when you look at how many magnetic lines of force is cutting across that squirrel cage like this in a circular fashion, it's the most it can ever be. So starting current is going to be way high. For a 480 volt motor, it's going to be 6 to 8 times your nameplate current. Your nameplate current and full load current are the same thing. And I'll have that written out. You ought to be able to print it out and follow me on this video take it. Please, please, please get your head wrapped around what I'm talking about here. This makes troubleshooting motor circuits so stinking easy if you understand how to check a motor, how to check your branch circuit conductors going to it, and how a motor works. You can take an ohm meter, megger, and an amp clamp and do more troubleshooting with those three items than you can imagine. This separates top troubleshooters from your parts changers, okay? So, you got the maximum lines of force cutting across this rotor. But what's gonna happen is, you're gonna start turning. This shaft's gonna start turning. Now, if it's a light load, this motor's gonna go whoom in 1 or 2 seconds, probably less than a second. It's gonna be full speed. The faster the rotor runs, it's catching up to the 1800 RPMs here. So as this speed comes up on the shaft, you're cutting less lines of force, the current has to go down, okay? Your motor current and your shaft speed are inversely proportional. When the speed goes down, the current goes up. When shaft speed goes up, current has to go down. It's like a seesaw. That's all you gotta remember. Now, no load current will be nothing connected to the shaft and the current that you draw. It will be less than nameplate current. Nameplate current or full load current happens when you have a load hooked to this shaft and you are asking for nameplate horsepower off the end of this shaft, okay? No load, nothing hooked to it. Full load will be when you're asking for, on this one, it's a 1 horse motor. So when I'm asking for 1 horsepower off the end of this shaft, if I had a hydraulic pump hooked to this, and that hydraulic pump, I could adjust a check valve and load it up and unload it. If I started out with no load and then I kept going until I was pulling, let me see what it's gonna pull, okay? 1.7 amps. 1.7 amps here. At 1.7 amps, we're asking for 1 horsepower work off the end of this shaft. 1 horsepower equals 746 watts. Write that down, tattoo it on your inner lip, okay? Your lower lip, whatever, because they're gonna ask you that on the test. 1 horsepower equals 746 watts. So when we crank that relief valve to the point that we draw 1.7 amps, we're asking for a horsepower work here. Now, what does that mean? It means something. We can take an amp clamp, excuse me, we can take an amp clamp, hook it on our motor leads or maybe over by our starter, which we'll talk about that too. And when we draw, if it's drawing 1.7 amps, we know we're asking for nameplate horsepower. Now, let's say that I keep cranking that relief valve down and this motor shaft slows down, slows down, slows down, slows down. As it's slowing down, the actual speed of the shaft is farther away from 1800 RPM of the synchronous speed. So where's the current got to go? If the speed goes down, current goes up. Speed goes down, current goes up. So we're going to pull more than 1.7 amps. We're going to start pulling 3 amps, 4 amps, 5 amps, excuse me, until we lock that rotor up. Now, when we lock that rotor up, we're going to be, excuse me, we're going to be pulling locked rotor current. Locked rotor current is 6 to 8 times nameplate current, okay? So, locked rotor and starting current are the same because when we start the motor, this shaft isn't turning. But the difference, it happens at different times. Now, if the shaft's locked and we try to start it and it doesn't turn, we're not really pulling starting current, we're pulling locked rotor current. But if we have a high inertia load means a flywheel. A flywheel is gonna start turning slower. It's gonna labor trying to get all that weight turning. Versus a little pump, boom, it's running. So, starting current may last a while for a high inertia load like a flywheel, or it may not last but just a fraction of a second, woof, in the case of a chemical pump or something. But when something happens, bearings in the motor lock up, the pump locks up, the load locks up, little Johnny put too much on the belt because he is the plant manager's nephew and screws up everything, and he put too much on the belt, so you're asking for more horsepower than the motor can put out, and it starts you ask for 2, 3, 4, 5 horsepower off a 1 horsepower motor on a conveyor, and pretty soon it stops because it can't pull anymore. Just like a truck or something, So then you're pulling locked rotor current, 6 to 8 times full load current, okay? These motor concepts are so important. Please, watch this again and again. Starting currents, when you start it, you're gonna pull 6 to 8 times full load current, but as the shaft speed comes up, the motor current will go down. When you are pulling nameplate current, you are asking for nameplate horsepower off the end of that shaft, okay? If you're asking for more horsepower than the nameplate horsepower is good for, then the shaft's gonna start slowing down, motor current's gonna go up, so instead of 1.7 amps, which is full load, we're gonna pull 3 or 4 amps and we got a problem. We're gonna overheat the motor, burn it up, trip it out, blow fuses, or whatever. So, if we understand that, we can do a ton of troubleshooting. You're gonna be adjusting the brake in the lab. I want you to watch for these conditions. I want you to study what starting current is, no load current, full load current, locked rotor current, nameplate current, excuse me. I try to use the same lingo that we use in the workplace. And that way, when you go out there, you're not gonna be thrown off whenever you're in that 2-hour job interview, right? That's what we want. We want you to get the job you want. Okay, watch this. Look for the handout that I've got on Blackboard, and we'll talk soon. See you in the lab. If I can get this thing turned.